Okay, for dynamic systems in which multiple processes simultaneously occur, the rate of processes that occur in them is a much better framework or a view or a measure for meaningful understanding and manipulation, not the amounts or volumes. The rate at which intercellular reactive species become available, the rate at which antioxidants scavenge the reactive species in the cell, and the resulting pseudo steady state level of the reactive species are the ones that need to be carefully looked at before big decisions can be made, and are much more useful than the cumulative amounts or concentrations of reactive species or antioxidants and so on. This we came to realize, okay, it was another discovery that we made when we looked at an antioxidant and its corresponding reactive species. For example, in this case, we looked at superoxide and superoxide dismutase because it is easy, specific. Superoxide dismutase is specific to superoxide, and therefore we could study the thing. What you have on the y-axis here is specific intercellular SOD level, which is superoxide dismutase level. This is activity. Okay. So, it is not enzyme which is not active, it is not a total protein amount, it is an enzyme, active enzyme amount, versus specific intercellular superoxide level. Okay. Moles per cell 10 power minus 14, you need to multiply these values by, right. So, what you see here is untreated is open circles. If you can make out an open circle somewhere, yeah, the error bars do not make the open circle very clear. These are all open circles, untreated, the relationship between SOD and superoxide. Menadione treated, menadione is known to induce superoxide in the cell, and curcumin treated, curcumin is a standard anti-cancer drug. Okay. We are doing these experiments with CIHA cells, which is a cervical cancer cell line. So, curcumin treated with our filled triangles. Typically, the thinking still in the literature is, going by the response in yesterday's seminar, is superoxide dismutase is a measure of superoxide. Makes sense from a molecular point of view, because the mechanism is known, it is supposed to quench this. So, you measure superoxide dismutase, it should reflect superoxide. No, there is absolutely no correlation, absolutely no correlation. Okay, not just this, every single study that we have done over the past 14 years, we first realized this 14 years ago, I will show you the first data also. We realized it in a different system altogether. And then that system I couldn't accept it. I said, repeat, repeat, repeat. Sir, this much data, there is absolutely no correlation. I said, fine, if that is the case, we will have to accept what it says, and which is good. It gave us a totally different direction to look at things. It was a discovery that, discovery in the sense, looking at it this way is incorrect. There is no doubt that superoxide dismutase quenches superoxide. However, levels in a dynamic system are a totally different aspect. So, this is in CIHA, this is in Chlorella vulgaris, which is a microalga. This is the first system that we recognized it in, right. This was the work which was done by Ranjani and Kavya mainly. With her data was when I realized that there is no correlation, and she repeated it, Ranjani repeated some of this, and then after almost 3 years, I think I accepted it. So, this is in Chlorella vulgaris, same set of experiments, and this is in Bacillus subtilis. Okay. So, you have Bacillus, right, a prokaryote, you have all the way to a eukaryote across domains, this behavior is seen. There is absolutely no correlation between superoxide and superoxide dismutase levels in the cell. So, all we are saying is do not use superoxide dismutase levels, which are easier to measure, much easier to measure than superoxide itself, as a measure or as an indicator of the superoxide level. The stress is caused by the reactive oxygen species. The oxidative stress is caused by the levels of reactive oxygen species, yes, there is no doubt about that. However, do not use an appropriate enzyme or even a coupled enzyme to indicate the level of the reactive species. Enzyme levels give their own inputs, that is fine, there is no problem. Do not match one and the other, do not relate it to the oxidative stress levels at that time. So, what is oxidative stress? So, these are three systems: Seha cells, which is a cancer cell line, cervical cancer cell line. This is Chlorella vulgaris, microalga, which we used for bio oil production at that point in time, and then Bacillus, which is a bacterium. So, oxidative stress in the cell, if the ROS production rate is greater than the ROS neutralization rate, the cell experiences oxidative stress, as simple as that. Okay, this is the fundamental definition or fundamental way to look at oxidative stress. Depending on its intensity, oxidative stress can have different and sometimes diametrically opposite effects on cell. It is called hormesis. At lower levels, actually it improves productivity. At higher levels, it kills the cells, right? And well known thing, at the lower concentration actually you have a more desired effect, and at a higher concentration it vanishes. And sometimes even at the higher concentrations it comes back and then vanishes, and so on. So, oxidative stress can have different, sometimes diametrically opposite effects on the cell. Surprisingly, low levels of oxidative stress can increase the growth of cells, the growth rate of cells, the rate of products made by the cells. Sometimes the cell can adapt to oxidative stress by upregulation of its counter mechanisms, can also become robust to higher oxidative stress levels in the future. When you treat it, it could become more robust in the future. It is called adaptive response. Higher oxidative stress levels cause damage to cellular molecules because they oxidize these molecules. The cell may be able to later repair the damage, but senescence, the cell is alive but cannot divide further, could result. Okay, all these could happen. At much higher levels of oxidative stress, cell death directly happens, either through apoptosis, programmed cell death, or even necrosis. If it is so high, it just damages the cell through apoptosis or through necrosis and other related mechanisms. There are autophagy and so on and so forth. So, other related mechanisms, cell death happens. So, this is typically the kind of response, the cellular response to oxidative stress from the context, from our context, from the context of production, from the context of medical applications and so on and so forth. These are the relevant happenings. At low levels it improves, you slightly increase it, it adapts, you increase it further, it causes senescence, it could cause senescence, increases much further, completely gone. Okay. Any questions, please? Any questions, comments, anything? Okay. Okay. So, remember that when we measure or when we measure the reactive species levels, because the standard difficulty with many classical biologists is that reactive oxygen species react very fast. So, what is the point in measuring it? You are not going to get its levels anyway. No, that is which is certainly true, it keeps on changing, but the pseudo steady state levels which you can measure at any point, which you measure at any point in time, whenever you measure, you are measuring only pseudo steady state levels, that gives significant insights into what is happening. Okay. So, that is what we are measuring. Okay. That is one important message to take away from the last part of the introduction. Should we start another thing today, or yeah, we have 10 minutes. 10 minutes is too much to lose. Okay, we'll start, my dear. We move on to the next chapter. Before this, any any questions, comments, anything at all? I don't know. I might as well take.
Measure these reactive species per level in the cell. So that is irreversible. So it just gives a diagnostic view. But the same cells we cannot use like further like cure. Right? We have to use like we just take a sample from the actual source. We cannot use what we've already used.
When you take a sample and measure the level of damage, so it depends on what you're measuring. See, if you use a biomarker, it gives you the level of damage that has happened. Use that data carefully. Use it. You say, if you say that this much damage has happened, which that is perfectly fine. But if you want to, so much of damage has happened, therefore you increase the dose so much to save the remaining part and so on and so forth, be a little careful with that. Depends. You need to carefully consider it. Carefully consider what information it actually gives. Whereas if you are measuring superoxide levels, it gives you the pseudo steady state level at that point in time, and so on. That's not so easy to measure. I mean, we have dyes; they are expensive. The superoxide is not as expensive as hydroxyl. Hydroxyl radical is very expensive. Dye is very expensive. I think the last time we paid some 43,000 rupees for 497 microliters. It's that expensive. That's where I use most of my project money on. So I need to take attendance. So good. It gives me an excuse to. So that is the what people do is they take superoxide dismutase levels and they say that indicates a level of oxidative stress at that point in time, and they base their therapy decisions on that. That is wrong. So this is today is what, 1st Feb, isn't it? Vikash is not around today. Okay. Lakshmanan is there. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 3 plus 6, 9. Okay. Okay. So next thing is we look at some reactions more from the point of view of how to analyze them. Okay. There are thousands of reactions involving reactive species. We are not interested in memorizing them and so on. Of course, they are important to know. So whenever it's necessary, you go and read up in books as to what exactly it is, how, and more complete, including electrons, including negative charges and so on and so forth. You need to get the information. Okay. But there's no point in remembering any of those, except that some you see them so often, the important ones, that you will remember them automatically. That's not a problem. So analysis of reactive species provides insights on their reactive species reactions, provides insights on their effects, how fast and how vigorous they are and so on. The basic tools frameworks available for analysis of reactive species reactions are well known. One is thermodynamics and the other one is kinetics. So this is something that we have picked up from basic chemistry courses right from the beginning, and emphasized on if you've done chemical engineering or biotechnology even to a certain extent. These two would have been separate courses that you would have taken. Okay. So because they are pillars of analysis of engineering systems, they give us all the information that is needed. Okay. So we look at some aspects relevant to reactive species in this class. So we look at thermodynamics. So which way should we do this? Okay, what we'll do is 10:46. We won't have time for that. We'll start with that in the class tomorrow. Okay, so it will give you it will help you refresh. I think you don't have to prepare and all that. Whatever you remember is fine. If you've done this, if you've not done that, that's okay. That's perfectly fine. You can pick up whatever is necessary from this. You've all done things in your higher secondary school level, basic chemistry, probably some physics and so on and so forth. So you don't have to worry about it. It's brushing up in case you haven't done an engineering course. If you've done engineering, it's essential part of it. It's just refreshing your memories. That's all. We'll start with that in the next class, right? Fine, then we'll meet tomorrow at 9 and take things forward and just finish off your attendance and then see you people. Any questions, comments before that?